So, good morning, everybody. Welcome to another wonderful day in the world of fluid mechanics. Today, we're going to continue our discussion on mass and energy balance as they apply to fluid mechanics systems. Now, on Tuesday, I left you all in the middle of a problem where we were looking at, I believe it was this problem here, flow through a pipe. When we're analyzing compressible flow, we identified that the mass in was equal to the mass out, and that simplifying the continuity expression left us the density 1 times the velocity at point 1 equals the density at 2 times the velocity at 2. So just for completeness, I kind of like that. We'll do blue today. We'll see how we all feel. So we had row 1, U1 equals row 2, U2. And the question was, what happens to density and velocity as the fluid moves through the pipe? Keeping in mind, we were really looking at compressible flow. So what do we think is going to happen to the fluid density as this system moves through the pipe? Is it going to increase, decrease, or stay the same? Anybody want to take a good guess? All right, y'all seem to be a little quiet this morning, I understand. Well, if we have fluid moving through a pipe, we had discussed previously that if we considered the pressure of the system, the pressure of the fluid would decrease. Through the length of the pipe. And since we can calculate the density as a function of the pressure, as pressure times molecular weight divided by the ideal gas constant divided by the absolute temperature, that means the density will decrease. Or row 1 is going to be greater than row 2. So if the initial density is going to be higher than the final density or the density at point 2, that means by the continuity equation, U1 will then be less than U2, or the velocity of the fluid increases. So let's look at an example of applying the continuity expression in a calculation problem. So let's look at this system here where we have fluid flowing through 4 different pipe sections. We have 25 gallons per minute. Let's just say we're looking at water. And Pipe section A has a diameter of 2 inches. Pipe section B has a diameter of 3.5 inches. C has 1 inch inner diameter, and D has 1.5 inches of inner diameter. So the question asks, what are the flow velocities and the flow rates for sections B, C, and D? So let's take a look at this one. So I'm going to write example 1. And I always like to draw the problems. That does definitely help. And I'm just going to draw like this, where I have my volumetric flow rate is 25 gallons per minute. My inner diameter in A is 2 inches. The inner diameter of B is 3.5 inches. Then I have C and D. This has a diameter of 1 inch, and D has a diameter of 1.5 inches.
Dr. Lopez, are you drawing? Because we can't see anything.
Thank you. I forgot to flip it back in the share. I apologize. So we have our system. So we need to find the flow rates of B, C, and D, and the velocities at B, C, and D. Well, we can solve for the velocity of A as the flow rate of A over the cross-sectional area of A, or 25 gallons per minute, which I would convert that to English units. So 1 minute is 60 seconds. There's 7.48 gallons in a cubic foot. And then to calculate the area of a pipe, that's simply pi times the diameter, which would be, in this case, it would be 2 over 12 feet, squared over 4. So I do this, and I should be left with feet per second. So doing this calculation, let's see what we have. 25 divided by 60 divided by 7.48 divided by pi divided by the diameter. We have about 2.55 feet per second. So for bonus, I can calculate A. So then the question is, to calculate B, C, and D flow rates, what do we need to know? Well, if we look at the continuity expression, what goes in must come out. So if we're looking at the flow rate of B, based on the drawing, I can say the velocity of B, or excuse me, the volumetric flow rate of B is equal to the volumetric flow rate of A, which is simply 25 gallons per minute. The tricky part happens when I want to determine the flow rates of sections C and section D. By the continuity expression, I know that the volumetric flow rates of C and D have to equal the volumetric flow rate of B. So the question is, how do we look at the breakdown? Well, as it's provided in the problem, one thing we have to understand associated with looking at this relative split is that if I'm a fluid particle in this system, what's more likely going to happen is I'm not going to see the split. A fluid particle is either going to go into section C or go into section D. There's not going to be a fluid particle that's going to come to the intersection and have to stop and make a decision. What that means is a fluid in this system is really going to see this in the problem, where you have section A at 2 inches, section B at 3.5 inches, and then a combination of sections C and D at 2.5 inches, where you have C in the top, D on the bottom. And that means the relative flow rates between C and D are only dependent on the pipe diameters as compared to the hole. And so I can calculate the volumetric flow rate of C based off of the relative area of C over the sum of the areas of C and D. And vice versa, I can also calculate D in this same manner. And that would be times the volumetric flow rate of B. So that tells you the relative contribution of that pipe area or that section over the total flow. So if I solve for the volumetric flow rate of C, it would be pi times 1 over 12 feet squared over 4 divided by pi 1 over 12 feet squared over 4 plus pi 1.5 over 12 feet squared over 4 times 25 gallons per minute, which if you do this calculation, you should get approximately 7.7 gallons per minute. Then by continuity, if you'd rather than doing this calculation, the volumetric flow rate of D would simply be the 25 gallons per minute minus 7.7 gallons per minute, which would be 17.3 gallons per minute. So I can go back up here and plug that in. I have 25 GPMs, 7.7 gallons per minute, and 17.3 gallons per minute. Now to find the velocities of each section, I simply have to take the volumetric flow rate of each section and divide it by the cross-sectional area of each section, which in this case would be the 25 gallons per minute divided by 60 to get it into seconds, divided by 7.48 to get it into cubic feet per minute, then 3.5 inches over 12 squared over 4. I'm giving you shorthand, but if you want me to put it out in full detail, let me know. I'm just doing it for the sake of time. And if you do this, you find that the velocity of section B is 0.45 feet per second. If you use the same approach for C, volumetric of C for the area of C, you get a velocity of 3.23 feet per second. And if you do that for section D, you get the same velocity, mainly because, as I said, the fluid doesn't see the sections as separate. So you get 0.85 feet per second, 3.23 feet per second, 3.23 feet per second. Now, I will make a caveat. This analysis of sections C and D is mainly valid because we don't have any information in terms of the energies associated with it. And when I mean by energies, I mean i.e. pressure. And so we're assuming that the pressure of the fluid as it enters these two sections are going to be the same, because all things considered, if everything's flowing steadily, they should be. However, if the pressures in those two sections aren't the same, we would have to look at our energy balance, and that would more likely cause a different distribution of flow between the two sections. So are there any questions or ways I can further clarify or demonstrate how we can apply the continuity expression in these kinds of flow systems. Hopefully you can kind of go ahead,
Can you
Jacob.
explain one more time why VB was equal to VA, the volumetric flow rate?
Sure.
Missed that part. Thank you.
Yeah. So if we're looking at a mass balance between section A and section B, right? Section A is 2 inches, section B is 3.5 inches. Like I said, I really like drawing. It really helps me understand things. So what I see in this system is all the fluid that's going into A has to go into B. There's no other area for it to exit, right? So if it's a mass balance, if this is my system, I drew a little magic box around that. All the fluid that's in A or flowing through the A box is going into B. And by that, I would say that all the mass that's coming into A is coming out of A and going into B. And from that, the volumetric flow rate of A equals the volumetric flow rate of B.
Okay, that makes sense. Thank you.
Of course. Hold on, my OneNote crashed. Give me a second to blow it back up. My laptop gets a little toasty when I do all of these things all at once. Any other things that I can clarify? I'm more than happy to.
I have a question.
Of course, Mitch.
So the velocities are the same exiting C and D, but their
Yeah.
diameters are different.
Yeah, the velocities are going to be the same in section C and D because, as I said earlier, the fluid's not going to see the division. It's going to go into section C, it's going to go into section D. So what's going to determine that relative velocity is going to be the combination of those sections. However, how much fluid goes into each section is going to be determined by the cross-sectional areas of those sections.
But that's what I'm asking. They do have different cross-sectional areas, but by the continuity equation, you're saying they're the same.
I'm saying by the continuity, the fluid's going to see it the same.
Right.
And so the velocities in each sections are going to be the same, but the volumetric flow rates are going to be different.
Okay. All right, I understand. Thank you.
Of course. Okay. All right. So that wraps up my introduction to mass balances, which means we get to start looking and discussing energy balances in fluid mechanics. Now, from 308, we can introduce a generalized energy balance over a representative system. And here I'll write it all out. And it would look like this, which means if I'm looking, let's just, my standard example, flow through a pipe, and I'm looking at kind of a representative slice of fluid within that pipe, I can define an energy balance associated with the mass flowing in, the mass flowing out, and the mass of the system itself. And there shouldn't be a dot there because that's not how this works. All right, so associated with the mass flow coming in and the energy that it brings, which is here, the mass flowing out and the energy that it's bringing in, which is here, and then the mass of the system itself. I'm guessing you guys can't see this. I apologize. Can you see it now? And so we have this differential energy balance over this system. Now, if we're going to assume steady state, we could say dm of the system equals 0. And the whole right-hand side of this expression goes to 0. And also, I can also, instead of considering a differential balance, I can then analyze this in terms of what I would call a delta, or a analysis between two states. And so if I rewrote the expression that I've developed, but instead of looking at the delta in minus out, the differential of in minus out, I can look at the deltas. What I'm left with is a delta U plus a delta P, 1 over rho, plus G times delta Z, because gravity doesn't change, plus a delta U squared over 2, plus a delta Q, plus a delta W equals 0. So let's talk about these energies terms in a second. So the first term we have is in, oh, I want a different color. I should let you all vote on what color I use each day. That'd be real fun. So this is the internal energy of the fluid. This is our pressure energy. This is our static or potential energy. This is our kinetic energy. Then we have our heat transfer and our work. That's either done on or by the system. So we have this expression. It looks slightly simplified, but we can do a little bit more. One thing I should actually point out, this is actually a delta of P, and the top P is pressure, the bottom is rho. So we have a delta over internal energy, pressure, static or potential energy, kinetic energy, heat, and work. Now from thermo, I can define our internal energy as delta Q plus F minus P 1 over rho. It would be delta 1 over rho. And what I can do is combine these two expressions into a single expression that looks like this. So basically subbing this in and doing some mathematical rearrangement, I can get an expression that looks like this. Where I have F plus delta Q minus P times delta 1 over rho plus delta U squared over 2 plus G delta C plus P delta 1 over rho plus 1 over rho times delta P equals delta Q plus delta W, which is work. So from this expression, I can then look and cancel out values or terms that appear on either both sides of the equation or that can cancel them out. So the heat term goes away, primarily because of how the heat transfer contributes to the energy balance and how the internal energy expression cancels out what we see in the initial expression. Then when I distribute this delta to both the pressure and the density term, what I'm left with is an expression where this delta 1 over rho cancels itself out, and what I'm left with is just a delta P over rho. And so eliminating those terms and then finally reorganizing this, I'm left with an expression that looks like this, where I have delta U squared over 2 plus G delta Z plus delta P over rho plus F plus W equals 0. And this is an extremely important equation. It's one of those really important ones that I'm going to throw all the colors of the wind at it. So here you go. Usually when you see this in the notes, it's one of those, you got to write it down. This is known as the mechanical energy balance for fluid mechanics. It's also known as Bernoulli's equation. Oh, that is terrible handwriting. I apologize. So let's take a look at this. We have the first term, which is a comparison of kinetic energy between two states. Then we have the second term, which is an examination of the static energy or energy associated with elevation. Then we have our pressure potential energy. The F is friction or frictional dissipation, and the W term is our work term. And so what this mechanical energy balance or generalized Bernoulli's expression states is, if we're assuming steady state and we're looking at an energy balance between two states of a fluid, the energy associated between those two states can be summarized by these 5 terms: pressure, potential energy, kinetic energy, work, and frictional dissipation. Now, if we assume that in a system, we can define it such that work and friction is negligible, we get an even simpler equation. Which states delta U squared over 2 plus G times delta Z plus delta P over rho is equal to 0. And this is what I call the simplified Bernoulli equation. This is what I usually refer to when I'm talking about the Bernoullis. But it's largely kind of dependent on what the textbook's doing and things like that. But what this system is saying is that if we're looking at a system that's at steady state and we can neglect work and friction, the energy of the fluid must be conserved And it must be transferred or exist as one of these three states, either in the form of kinetic energy, of static potential energy, or of pressure energy, which we can talk about whether pressure energy is potential or not. I would consider it a potential energy. Some people don't. But definitely another one of those. Circle, put it in your equation sheet. Do whatever you got to do. So is there any way I can further clarify how we were able to look at a generalized differential energy balance over a volume element in a system, and based on some key assumptions, using thermo principles to get rid of internal energy because nobody wants to calculate that, we can arrive at both the mechanical energy balance, generalized Bernoulli expression, or the simplified Bernoulli equation. Two very important principles that we will be using a lot of over the next 4 or 5 weeks. So if there's one thing that you're gonna have mastered by our discussion of fluids, I really hope it's this.
Hey, Dr. Lopez,
Yes, sir.
I had a question. So when you had it listed in the green with all the energies, and the next step, you moved the Q and the W over. You just
Yes.
moved the other side of the equation, but shouldn't it be negative there? Or was it supposed to be negative before?
That's a good question, and it's one that I usually expect. And we can talk about it right now. In terms of work and heat, the short answer, the TDLR, is the signs don't matter on these terms. And that really makes people mad, especially people that like math, because, signs mean everything, but I'm an engineer and I said that's cute. What we look at, especially when it comes to work and heat, is convention. And what I mean by that is in these expressions and in the energy balance, work is going to be negative if it's done on the system. Meaning if I have a problem that's got a pump that's supplying power or a compressor that's supplying pressure energy, so that's usually what pumps and compressors do, I'm going to consider that work negative. And work is positive if done by the system. This is going to be in the case of, turbines, where you're wanting to generate energy or take energy out of the fluid. And so heat also applies in the same way, but if I'm honest, heat is completely the opposite. Heat is positive if it's done on the system, and heat is negative if it's done by the system. I usually don't give you the heat convention until we really start getting into it, but that's why, honestly, largely the signs that we use in those terms don't matter. And let's further exemplify this. So for my full mechanical energy balance, I have all these deltas, right? So a lot of times we end up writing the expressions like this when we're wanting to compare it between two states. Where I'm looking at U1, which is an initial state, and U2, which is I'm in a final state. So in this expression, This is my final state. And this is my initial state. I see a chat. I'll look at it here when I finish this explanation. So if I'm looking at a system and I'm going from my initial state to my final state, friction in this case is going to be positive. Work in this case on this side of the expression is going to be positive. Now, if I moved it back to the original form where I had, you know, everything on the left side, it would look like this. As it's originally written, now it would be negative because it's on this side. Where the delta is looking at, you know, state 2 minus state 1, or the final minus the initial. That's the conventional we do an analysis over 2 states. And so when you're looking and solving for work requirements for pumps and compressors, your final answer is going to be in a negative. Because initially, if you look at the system without these two terms, you have the simplified Bernoulli, where we just have kinetic energy, static energy, and pressure energy. And if there's no work or friction, those two energies should equal the same value. Now, if we put in work, if we're going to use a pump to do more work, that energy should be added to the initial state to get to our final state. And if we don't have work, and if we just have friction, that energy, well, actually, this will be negative. I apologize. Should be removed from the initial state to get to the final state. And so for a lot of the terms, I'm not necessarily concerned, especially when it comes to these final for a few terms. The signs don't matter because it's better to understand how they contribute to the energy balance as a whole than whether the sign should be positive or negative. So looking at these states, work should add to the initial state's energy to get to our final state's energy. Friction's going to reduce the energy of our final state. So work is going to be positive in this sense on this side and negative on side, and then it's going to be vice versa on the other side of the expression. Does that help explain that circumstance? It's a little odd, and that's why I say I know some people it really frustrates them in terms of what sign to use for these terms. All right, so and another question, if I clear, what's the subscript for Z and G delta Z? Could you clarify what you mean by subscript?
Yeah, so it just looks
Oh,
kind of,
it's
yeah.
a 2, sorry. My pen, this should be a 1. I'm looking at initial and final states. Sorry, my 2's and Z's look the same. That's why when I do Z's, I try to put a line through it to differentiate it between my 2's. So yeah. Also, a quick note, since we talked about work, let's talk about power. We calculate power for these systems by this expression here, where power is calculated as a function of the mass flow rate times the work required over the efficiency of our energy transfer device, i.e. our pump or compressor. Now, keep in mind, power should always be positive. So even though you'll find a work term that's negative, get rid of the sign when you calculate your power, because it's just not going to make sense. Also, speaking of not making sense and frustrating students, the units of power Well, in the SI system, it's simple, it's watts. In the English system, we use horsepower as the most standard convention. And for horsepower, 1 horsepower is equal to 550 foot-pound force per second. So you have to be extremely careful when you do calculations associated with power in the English system. And yes, I'm going to make you give me power requirements in horsepower because some pump manufacturers, that's all you get. You get 1/4 horsepower pump, 1/2 horsepower pump, 3/4 horsepower pump, 1 horsepower pump, depending on the sizes. So you're going to have to know how to identify power requirements for fluid systems in that regard. And so let's take a look really quick, at this system. So what are the units of each term? Because they're all being added together in some form or fashion, so which means by, unit laws, they all have to have the same units. So what are the units of each of these terms?
For English, would it be feet squared per second squared?
Yeah, so it would be feet squared per second squared, or in generic terms, I would just say length squared over time squared, which means your work is going to be a feet squared per second squared. And if I'm calculating power, I'm going to multiply that times my mass flow rate, which means I'm going to have a pound mass per second times a feet squared per second squared, which is going to give me a pound mass, feet squared, per second cubed. Now that's a bunch of gobbledygook. So in order to get to the right unit, I'm going to therefore have to divide by G sub C, which is going to be in my 32.2 pound mass foot per pound force second squared. I do that, and then, and only then, am I left with foot pound force per second. So if it helps when you're looking at your power equation, you can sneak in that G sub C right there to let you know that you're going to have to do some unit conversions. Also, since we're on the topic of unit conversions, our delta P over rho term should come into a length squared for time squared, which means in English we should have foot squared per second squared. But if we're in English units, a lot of times our pressure is going to be PSI. So what we're going to have is a pound force per inches squared over a pound mass per cubic foot, which doesn't really play well together. What that means is when you're bringing in pressure, particularly PSI, into these expressions, you're not only going to have to multiply by G sub C, pound mass, foot per pound force second squared, you're also going to have to convert the inches squared into feet squared. And then and only then will the units work out. So you have to be careful on that term. Any further questions? Let me know if I'm going too fast. This is where things get lots of fun. Where the units like to explode and the signs don't matter. All right, let's look at a question and we'll talk about it. Go away discussion. So I have a fluid moving in a pipe, assuming the simplified Bernoulli equation, meaning there's no work or friction. So the question I'm asking, is the pressure at point 2 going to be higher, lower, or the same than the pressure at point 1? And the way I've drawn it or attempted to draw it is the diameter at point 2 is going to be larger than the diameter at point 1. So I'll tell you what, I will give you guys 2 minutes to talk about this in a breakout. And then you can come out and give me an answer and maybe even an explanation. So I'll give you all like 15 more seconds to write it out. And then I'm gonna throw you into the void. All right. I'll see you all in a few minutes. I always wonder when the people that are still here, either if they're like at the bathroom and they're not paying attention, or the breakouts just don't like them. How are you, Elahe?
I'm good, Dr. Lopez. How are you?
All right. Oh, you're walking to campus.
I was like, the funny thing is that we don't have a shaker in the pharmacy lab, so I have to come all the way to Anderson to put my samples in the shaker. So that's where I'm walking back from.
Oh, is it the shaker that we have in 224?
Yes.
Well, if you want, you can probably just borrow the shaker for a while and put it in the pharmacy lab. I'm fine with that.
It's yours?
It's not mine, but I don't know who it is. I can see if anyone else is using it, and if not, you're welcome to borrow
Yeah,
it.
that would be nice. Yeah, because I like walk back and forth.
Yeah.
Yeah.
Especially in today's day and age, I would like to limit your movements. Speaking of, how are you feeling?
I'm good. They actually called me back yesterday and told me my test was negative, but they still told me to come in tomorrow to like check if I I don't know, to check, do a checkup.
Do a checkup. Now that you're negative, they'll actually see you instead of poke you from
they
a
would
distance
actually
with a
let
stick.
me in. Yeah, they wouldn't let me go into the building. They have like a tent set out outside, and they will like test you outside of the building.
Fun.
The new age, Dr. Lopez. The new age.
It is a new age.
Did you get new students? I saw like Dr. Naranian's post in LinkedIn about wanting 2 new students.
We have one. We're trying to get the second for our project.
Oh, really? You have one already? That's nice.
Yeah.
When is they're joining?
They're already there. They're just, trying to figure out when it's safe to come in. I'm gonna have him work with ChE to get acquainted in the Adams lab, because he's gonna be mainly working in that pharmacy lab.
Oh, okay. That was like what ChE was telling me, that he had, like there's a new student.
Yeah.
Okay.
He's gonna have to get him trained up.
That's nice.
Yeah. Well, I'm
So
glad
he's
you're
American,
feeling.
Right?
Yeah, he's a former student who graduated not in May, but the year before. It was kind of one of those, we weren't sure, but we're gonna give him a chance, and also we need a student, and there's no way we can actually bring anybody in.
Yeah, Makes sense.
outside of a tunnel on the south side of the border.
Well, I hope it goes well.
Yeah. I'm glad you're feeling better.
Thank you.
All right, let me see if I can bring everybody back and we can talk about this. Everybody's coming back. Oh, it's because I don't have the right textbook. That's helpful. Welcome back, everybody. I think we got most everybody. So, who would like to volunteer and give me their solution and justification for what they thought for this question too? I'm assuming you guys can still see it.
Yes, we can see it.
Wonderful.
Did you want us to justify our answer mathematically, or was it more conceptually? Because we were doing more of like the conceptual side.
Conceptual is fine with me.
Okay.
Would you like to volunteer, Claire?
Yes, well, Mitch Vaughn told me to
Oh.
earlier, but no, it's okay. I'm fine with it. So when what we're assuming is that volumetric flow rate remains the same, or the fact that we assume that it was a Newtonian fluid, so we just assumed that rho was 1 or was unchanged, so we just made that equal 1 in the Bernoulli equation, and then with we said that pressure would decrease at 0.2, and mathematically speaking, it's going to be force per area, and so when your area is larger, the quotient is going to be therefore lower. And then more of like a physical sort of explanation, we said that when the area goes up, the volumetric or the velocity has to go down for volumetric flow rate to remain the same, and when velocity goes lower, that means that there should be less kinetic energy of the particles to bump into each other, and therefore the partial pressure of the fluid should be lower, and therefore the pressure at 0.2 would be lower.
Okay, I like it. Anybody else? Everybody agree? Yeah? Thumbs up, thumbs down? Yeah? We don't know? Let's take a look. I would say I like most of your explanation, but you're missing a key point. So let's take a look. So we have this, return of the civil engineers making their wrong types. So we've got some area here, some velocity, area, velocity. I like your assumption. Newtonian. We got an incompressible fluid. On Earth. Got to make sure all those assumptions are known. And so if we're looking at the continuity equation, I can say rho 1, U1, A1 is equal to rho 2, U2, and A2. Doing that comparison between states. I said it's an incompressible fluid. And so my densities will cancel, which means I'm looking at a comparison between my areas with my velocities. And since the area is increasing, so since A2 is greater than A1, that implies U2 is less than U1. So you're right in that regard that the velocity is decreasing. Now let's look at the Bernoulli, or the simplified Bernoulli expression. I have delta u squared over 2 plus g delta z plus delta p over rho equals 0, because I'm assuming, once again, assuming no work or friction. We don't want to deal with friction yet, trust me. And so if I spread this out, I have delta u2 squared minus u1 squared over 2 g times z2 minus z1 plus p2 minus p1 over rho is equal to 0. Now if I assume no elevation change, z2 is going to equal to z1. So this is going to be 0, and I'm left with this expression here. u2 squared, oop, wrong color, all right, so now I have u2 squared minus u1 squared over 2 plus p2 minus p1 over rho is equal to 0. So we already found by the continuity expression that the velocity has to decrease, right? So is this term going to be positive or negative, this first kinetic energy term?
It should be negative.
All right, so this term's going to be negative. So what does that tell us for this second pressure energy term?
It has to be positive.
Okay, so the second term has to be positive. So if the second term is positive, what does that tell us about P2 in relation to P1?
It should be greater than P1.
So P2 is going to be greater than P1, or the pressure energy will increase. So by continuity, since we're increasing that flow area, the velocity is going to fall, which means the kinetic energy of the fluid is going to decrease. But since we're assuming there's going to be no frictional dissipation or work, that loss in kinetic energy has to either go into static energy or pressure energy. If there's no elevation change, there's no way it can go into static energy. That means the energy will then be transferred as into pressure energy, or the pressure will increase at point P2. Yeah, this one's it's a little funky because in general, fluid's always going to flow from a high pressure to a low pressure because that's the driving force for fluid flow. But in some of these situations, they can be designed such that the pressure is going to be higher on the back end, but at the same time, this is a simplified and idealized situation where there's going to be no friction. When we bring in friction, that it's going to be unlikely that the pressure is going to be higher in this sense. However, for the exercise that I've developed here, it will be higher. All right, so let's look at some examples of doing calculations with the mechanical energy balance. So now let's say I've got N-pentane being transported from a supply tank to a storage tank through 100 feet of 3-inch piping, assuming a pretty large elevation increase of 40 feet. And if the mean velocity of the pentane is booking it through the pipe at 25 feet per second, let's see if we can determine the following values. With N-pentane flow rate, the power to drive the pump, and the pressure at the pump outlet. So let me draw this for you, because I will admit sometimes when I write out some of these problems, it's hard to visualize. So let me share with you what I take from this problem statement. So I've got a storage tank, or a supply tank to a storage tank. So we're looking at N-pentane transport. So I've got a supply tank. I'll leave it open to the atmosphere, it makes my life easier. And I've got a pump, and I'm going to a storage tank. Maybe it's a little bit bigger. And the way I see these, the length of the pipe is 100 feet. The inner diameter of the pipe is 3 inches. My delta Z is going to be 40 feet. And my velocity is going to be 25 feet per second. So let's see what we can find first. Well, we can probably find the volumetric and mass flow rate first. Knowing the volumetric flow rate is the velocity times the area, which is simply the velocity times pi times the diameter of the pipe squared over 4, which in this case would be 25 feet per second times pi times 3 over 12 feet squared over 4. So this gives us our volumetric flow rate in cubic feet per second. And I get about 1.23 cubic feet per second, which is actually quite a lot. And to get the mass flow rate, it is simply the density of the fluid times the volumetric flow rate, which I didn't give you a temperature, so you can assume a standard temperature. And doing a quick search for N-pentane density, I get about 626 kilograms per cubic meter, which should be 39 pounds per cubic foot. So I have 39 pound mass per cubic foot times 1.23 cubic feet per second. And so my mass flow rate is going to be 39 times 1.23, or about 47.9 pound mass per second. So we've got those two values determined first. So the next thing we need to look at is the power to drive the pump, meaning how much energy do we have to put into the system to get the fluid from the supply tank to the storage tank. So this is where it gets a little weird and funky, primarily because when you're looking at doing energy balances and Bernoulli balances, you have to, quote unquote, pick points in your system. And when I do these, more often than not, I'm going to pick points that look like this. So the top of the supply tank and the outlet of the system. So with that, I can draw a Bernoulli balance. So I have delta U squared over 2 plus G delta Z plus delta P over rho plus work plus friction equals 0. Now in this problem, for now, I'm going to assume that there's no friction. There is going to be work because I've got a pump involved. And so that's the only real assumption I can make in this system. So at this point, what I like to do is then I like to bring out each term in the expression and identify if there's any additional values that I can neglect. So now I have u2 squared minus u1 squared over 2 plus g times z2 minus c1 plus p2 minus p1 over rho plus work is equal to 0. Well, now let's look at each term. U2 would be at the fluid velocity as it is discharged into the storage tank. Now, that value is already given, and it's going to be the 25 feet per second because we know what velocity it's flowing at. U1 is going to be the velocity of the fluid within that supply tank. Now, we can discuss what that velocity would be realistically, but for all intents and purposes, I would say that that velocity at the top of that tank is going to be negligible, such that that velocity is 0. The elevation, z2 minus c1, was already provided to us as 40 feet, which leaves us with our pressure term. Now, if I assume that both of these tanks, both the supply and the storage tank, are non-pressurized or open to the atmosphere, P1 is going to be about an atmosphere, and P2 is going to be about an atmosphere too. So if I'm interested in knowing the pressures, I can know them, or if I can assume that they're non-pressurized, this value goes to 0 as well, and I don't have to worry about what those pressures actually are in this sense. And so what I'm left with now is u2 squared over 2 plus g delta z, and I'm going to put a delta z because it's already given as a single term, plus work equals 0. I know my velocity is 25 feet per second squared over 2. Gravity in English units is 32.2 feet per second squared. My static term, as identified, the delta z, is 40 feet plus w equals 0. Now both of these two terms are positive, which means my work, when I bring everything over to the other side, is going to be negative. So I have 25 squared divided by 2 plus 32.2 times 40, which gives me a work term of 1,600.5 feet squared per second squared, or 1,600 feet squared per second squared. And it's going to be negative because it's done on the system. Now I have my work term, I can solve for my power. So I identified my mass flow rate earlier as being 47.9 pound mass per second. I have my work term, which is 1,600 feet squared per second squared. I have to do with my unit conversion, 32.2 pound mass feet per pound force second squared. That gives me my solution in terms of foot-pounds per second. Then if I divide by 550 foot-pound force per second, I am left with horsepower. And if you want, we can assume an efficiency. I'll say it's 0.8 for good measure. So I do this calculation, and I'm sure it's going to be a fairly large pump. Yep, it's going to be 5.95 horsepower, which I would say it's a 6 horsepower pump and be done with it. So it's pretty beastly. Are there any questions on how we determined the power as well as the work, how we looked at the energy balance and asked ourselves which terms could be canceled based on necessary assumptions we can make? It gets really tricky, like I said, picking those points. So never hesitate to reach out to me and ask, okay, I don't know where to start this. What would you pick in terms of points? Primarily, if we're looking at this second, or excuse me, this last thing it asks us to identify is the pressure at the pump outlet, which means now we're going to have to go out and pick a third point and do another Bernoulli, either looking at 1 and 3 or 3 and 2. I'm most likely going to look at 1 and 3. So to find the pressure at the pump outlet. Which means if I write out that Bernoulli again, I'm left with this. Now, once again, I would say my velocity 1 is negligible. What I can also say is if I want to assume, once again, that that pressure 1 is going to be open to the atmosphere, I can then say P1 is 0 gauge pressure and say I'm going to do these calculations looking at gauge pressure. Now the delta Z is tricky. How I drew it, you can say, well, there might be some elevation in terms of the liquid level in the supply tank versus the pump, which can. So for all intents and purposes, I'm gonna say this is gonna be negligible as compared to the 0, just to make this a little more simple. We can have discussions, and this is where if this was a real situation, you would really want to know what that elevation is to make the most accurate assumption calculation. But for all intents and purposes, and since we only have a few minutes left in class, I'm going to say that delta Z 0, and fully admitting that that's really not going to be the case. And so what we're left with is U3 squared over 2 plus P3 over rho plus W is equal to 0. Now U3 is going to be the same velocity because I'm assuming the pipe all has the same diameter. And so I have 23 feet per second squared over 2 plus P3 over rho plus W equals 0, where W, once again, is that negative 1600 feet squared per second squared. And so what you should find out is when you do P3 over rho, this value should be 1600.5 minus 312 over 5.5, or about 1,288 feet squared per second squared, if my pen would work with me. Which means to find P3, I would multiply by the density, which we had earlier, which I believe was approximately 39 pound mass per cubic foot, times 1,288 feet squared per second squared. And I need pressure, probably in PSIG. So I'm going to divide by 32.2 pound mass foot per pound force second squared. And then I'm going to divide by 144 square inches in a single square foot. And this will leave me a pound force per square inch, or PSI, And since I made an assumption engaged, my answer would be engage as well. So doing this calculation, I should be left with approximately 10.83 psig. So that is the pressure above atmospheric, excuse me, that fluid leaving the pump would exhibit. All right. Are there any questions over that example and how I was able to use the mechanical energy balance and Bernoulli's to analyze the system, identify which terms I can neglect, figure out which terms I needed, plug in and solve for both work, power, and also pressure. This is one of these types of problems that I'm going to throw a lot of different variations at you at, and so you're going to get lots of practice.
Is there a reason why you chose the pump to be at 0.3 rather than the end being 0.3?
No, that was just how I did it. Yeah, there was no big reason why. It's just when I do it that way, it's just be kind of the order of operations. Yeah, the pump could have been 2 and the outlet could have been 3. That's just convention and how I made up the problem. All right, if there's no more pressing questions or concerns, that's all I have for you all today. So next week we'll do a little bit more in Bernoulli's as well as start jumping into momentum balances. One thing I will kind of give you all a heads up on a couple things on momentum balances. One, I would say it's probably one of the most difficult concepts associated with fluids. So don't beat yourself up if it doesn't come instinctively. It's one of those where it takes some thought and some mental exercise to kind of grasp. And 2, I'm not sure if we're going to get through it all next week. So if I feel that's the case, I will adjust and update the module content for 3 as well as the homework and things later on next week. But the module 3 will be released this afternoon, so you can kind of take a good look at momentum. But just kind of know going in, it's kind of a weird animal. All right. If not, take care, guys. Thank you all for coming. Have a great rest of your day and a great weekend.
Bye, Dr. Lopez.
All right. Bye, guys.
Bye.